Okay, so limit comparison test is a little less intuitive than direct comparison, but through just a little explanation, it should be kind of clear. So our postulates for this one are k and z are finite numbers, and c is a value in question. So if we multiply c by a finite number and we get another finite number, it's also that means c must be finite. Like you can't say 3 times 5 equals infinity since they're both finite numbers. But like what are you to say that this equals? You can't say that this equals 5. You can't say that this equals a finite number because you're multiplying a finite number by, whatever this is. Um so that's also how we say that if k is finite, like 5, and we multiply it by infinity, it'll equal some sort of infinity, which means, then this would be true. And if we don't know what it is, if it's just c, then, well, it has to be infinity, because that's the only thing you can put in there for that to make sense. So c is some sort of infinity if, when multiplied by a positive constant, it is infinity, and is some sort of finite number if, when multiplied by a finite number, results in a new finite number. Um, so let's look at these series. So this one should be really easy to understand. It's just the P series. If I told you to do it earlier, you'd get a finite number. Actually, I might link the video in some sort of description for this, but this actually equals pi squared over 6. There's a really good geometric interpretation for this on 3 Blue 1 Brown's channel. Yeah, so this actually just converges to pi squared over 6. Which all you really need to know is that it's a finite number. You don't need to know that for the exam. I just think it's cool. But if we want to show this, if we take the limit as these two series approach infinity and divide them, what we're essentially doing is showing the limit as n approaches infinity. That does not look like an infinity of k over, or I guess this would make more sense as, or no, it would be z, which is our, actually, let's just like write them up here. So z and c. C is what we're trying to find. Z is something we know is finite. So if we get z over c, right, we're taking essentially that limit, and now we're going to get uh now we're going to get a k value out of it. If our k value is finite, well then our c value must be finite since we know that our z value is finite. If our k value is infinite and we know our z value is finite, then that means c must be infinite. So if you actually evaluate this limit, I would let you do it yourself. You can like pause the video and whatever. I don't feel like wasting your time evaluating it myself, so I'm just going to write it out. This equals 1 over 16. And 1 over 16 is finite. So that means although this is only looking at what we would consider the last term of the series, what we notice is that this converges to this value. It goes towards 1/16th. So for every like value, especially at the end of that series, it's just being multiplied by a finite number, which is mathematically the same idea as if you multiplied by the sum by a finite number. So we know that it's 1/16th. C is finite, so we can say that the series described by B converges because it's finite. So B converges. The other big idea is that if it's infinite, if Z is infinite, the other idea I didn't explain too thoroughly is that if the opposite happens, if say I have some A divided by B in that limit and approaches infinity, this, if this approaches, I don't know, some k value, but both of these are, but one of these is infinite, the one that we know is infinite, and we have an unknown right here. What we have to say is that b is also some sort of infinity. It's just, I'll call it infinity not. I think another big thing to wrap your head around is that not all infinities are the same. If you take infinity and you multiply it by some positive k, it's still infinity, but like these two things aren't equal to each other. They are both describing very similar things, but it's a different infinity. You don't need to do math with them. It's just a conceptual barrier to understanding things like this, where, oh, if you have infinity and you divide it by another infinity, you can get a positive value. Actually, you do that in L'Hopital's rule. You divide infinity by infinity and get a positive value sometimes. It's just these infinities are different from each other by a factor of k. So if you know one of them diverges and you don't know the other one, and then you do the comparison test and you get a finite value, you say that the other one diverges too. Other ideas, the barriers you have to go through before you can prove that you can use the limit comparison test. The idea is that it must be a positive, both need to be positive series, and the denominator cannot be less than 0, and the value you need to get has to be positive and finite. I explained finite, I didn't explain positive. Positive is a little weird because if you have a series that's always negative, it will actually work completely fine. It's just when you have series that alternate, the issue becomes, oh, you don't know whether like you don't know whether that k value is positive or negative, and it could constantly be switching at the infinity point. And if that happens, you can't really use this test. Another thing is, people always ask me in class whether it's a of n over b of n or if it was b of n over a of n. The answer is that it doesn't matter, because let's say this goes to a finite number, 3. Okay, well then this would go to 1/3, which is still a finite number. These are the same. It doesn't matter which one you choose as long as it results in a finite number. And then say potentially went to infinity. If you did it the other way around, it would still go to infinity, or it would go to 0, which is not a positive number. Another thing is, with positives, it can't be 0. If the limit is 0, then it gets really confusing.